Szanowni Państwo, witam Państwa serdecznie.
Good evening. Welcome to an evening of lectures with our French experts, which we have prepared in cooperation with the French Institute and the Embassy of France. We would like to welcome Jean-Luc Schneider, ambassador. Professor Schneider will deliver a short introduction to the French experts and lectures. Thank you very much. Merci.
All. Unfortunately, I am just unable to speak in Polish. On the occasion of the Przemiany Festival, we are meeting tonight in this beautiful auditorium of the Copernicus Science Center in Warsaw to listen to scientific lectures given by two French scholars. First of all, let me introduce myself. I am Professor Jean-Luc Schneider, the new attaché for science and higher education at the French Institute in Poland and embassy also. I am a geologist. So let me have the pleasure to talk to you very quickly about Earth sciences, because it is in some way the subject of the lectures tonight. These are sciences that are resolutely turned towards the past. They allow us today to make some observations. Since its origins, 4.6 billion years ago, our planet has always undergone important changes. During this long history, the evolution of the atmosphere has also undergone major changes. For example, around 2.5 billion years ago, among the first living organisms, photosynthetic bacteria, the stromatolites, enriched the atmosphere of the Earth in oxygen. The climate also had many episodes of slow change over time. For example, 100 million years ago, the average temperature on Earth was 25 degrees. And there was no ice anywhere for a very long time. We can also study the climatic variations of the last 2 million years from the contents of greenhouse gases, such as carbon dioxide, trapped within bubbles of ice in Greenland or Antarctica. These gases control the atmospheric temperature. From results of their analysis, we then realized that the recent climate has undergone a succession of ice ages with interglacial episodes. Temperature changes have always occurred slowly over long periods of time, up to several thousand of years. But Earth sciences are also concerned with understanding the present and possible futures. Today, the average temperature on Earth is 15 degrees. Thus, the present-day climate is pretty cold. But unlike the recent ice ages, the present-day increase in greenhouse gases in the atmosphere, although similar in magnitude to those seen during the ice ages in the last 2 million years, the changes today is occurring in less than 2 centuries. This is much faster than during natural variation. Human activity are at the origin of this terrible kinetic. Therefore, man also contributes, like the stromatolites 2.5 billion years ago, to the modifications of the atmosphere. This observation alone justifies the Przemiany Festival and the urgent need for reflection to identify new solutions for the near future. It is interesting to note also the coincidence between the holding of this festival and the awarding of the Nobel Prize in Physics this week for the discoveries on climate change modeling. The first lecture tonight will be given by Professor Valérie Masson-Delmotte, who is a specialist in past and future climate change. She is a member of the Intergovernmental Panel on Climate Change and will talk about the latest report written by this group. And this report analyzes the present-day climate evolution and its consequences for the future. Then, historically, Earth sciences have developed because of the exploration and extraction of raw materials. This is why these sciences are still very much concerned with these issues today. This extraction has important environmental consequences and weighs on the geopolitical balance on a planetary scale. This is the subject of the second conference presented this evening by Guillaume Pitron, journalist and writer. This lecture is devoted to the major issues of the exploitation of rare metals, whose role is fundamental in the development of new technologies and which cannot be dissociated from the climate issue. The Przemiany Festival is a very important event to feed the debate on these central topics. This is why the French Institute and French Embassy support it. I wish you an excellent evening and thank you for your attention.
Thank you very much, Professor Schneider, for this introduction. Myślę, że już mamy na
And I think we have Professor Masson-Delmotte with us. Do you think we can begin?
Yes, Professor, we can hear you loud and clear. So the screen is yours. Thank you.
Thank you very much for this invitation, and I wish I could be physically with you. My last visit in Poland was 3 years ago, at the time of COP24. Many things have changed over the past 3 years. And one example is that we have delivered one new assessment of the state of scientific knowledge regarding the physical stage of climate change. In this presentation, I will share some of the major highlights from the 2021 IPCC climate report. I will place an emphasis on the way this report has been prepared through what I describe as a co-design process, what we have implemented to facilitate the broad participation of scientists from around the world in the preparation of this report, and how the needs of climate information to inform action has been considered throughout the preparation of the report. I have to explain that this report by itself does not develop new knowledge. It is an assessment of the state of knowledge from the critical examination of more than 14,000 scientific publications. And I have to acknowledge the dedication, the amazing dedication of 234 authors from 65 countries, hundreds of contributors, thousands of reviewers from the scientific community and experts nominated by governments, who have provided more than 78,000 review comments. And it is that process, that peer review process, which is critical to provide you with scientific knowledge that is rigorous, robust, exhaustive, and it is done in a transparent way so that you can trace each conclusion to the assessed evidence from the scientific literature, and each finding in the report is expressed with a level of confidence. Why do I speak about a co-design process? Because at the beginning, when we design the structure of the report, we run numerous consultations and surveys to analyze what are the needs expressed by delegates from all governments in terms of scientific information. And I would like to flag two examples. The first one is the need for regional climate information, as it is critical to inform risk assessments and adaptation strategies. The other example is multiple requests to have climate information, not just in the coming decades, but also looking at irreversibility and projections beyond several centuries in the future. This scoping has led to the design of the structure of the report. We have then run a call for participation of scientists. We have received more than 1,000 nominations. It was really difficult to select the small author team. And we did that by the following principles: 2/3 of new authors, a balance of expertise by analyzing the publication track of the scientists, some of the brightest experts focused on one area, and more experienced scientists with a broad overview of multiple aspects of climate science. We have brought on board the bright young generation of climate scientists, including from developing countries, especially from Africa. When we had the first meetings of the authors, it was clear that even if you bring together the brightest minds, you still face obstacles to their full participation. So we also brought on board specialists of participatory and inclusive practices, so that the team of authors learned how to work together when you are not always native English speakers, when you have different cultures of how to work together. Some are more familiar with open brainstorming processes. Some expect to have clearer guidance from the coordinators. So we took this into account to facilitate the participation of scientists from multiple countries and cultures. The third dimension is integration. The IPCC has released 3 special reports in the last years on what does it take to limit warming at low levels, 1.5 degrees Celsius, on the ocean and cryosphere in a changing climate, and on climate change and land, looking at physical climate change, but also impacts and risks, and solutions in terms of adaptation and mitigation. This allowed us to have a clearer understanding of the handshakes between what we can provide in terms of physical climate information and information needs related to adaptation, related to mitigation. This is also reflected in the design of our report. And of course, as you know, in the past 2 years, we have all been hit by the COVID-19 pandemics. So we had to move to virtual work. It has been a challenge, but we have learned from our participatory and inclusive practices. We have implemented new practices to continue to work virtually. and we only had a 4-month delay in the release of our report. And for the first time, we also had an online approval session with delegates from all governments, the authors of the summary for policymakers, which is the high-level summary from the report. And we spread the approval process not just over 5 days in the same place, but over 2 weeks, taking into account the challenges with working across time zones. It required much more planning, but at the end, it was flagged that this was one of the most successful approval process ever. And if you are interested, you can find the report from external observers that describe this specific approval process, which is critical for our summary to reflect in a balanced way the key findings from the thousands of pages of the report itself, and to express these findings in a very clear way. For instance, we were asked to provide more details on the various types of droughts, which are so critical for water security, for food security, in many places around the world. And this is one example of that co-design process. This information was available, and it was asked by governments to place a stronger emphasis on the different types of droughts in the final summary. In this report, we bring together multiple lines of evidence. Of course, insights from observations of our changing climate, trends and extremes, understanding of the feedback loops that shape the response of the climate system when we alter the energy balance of planet Earth, understanding the relationships between drivers, responses, so causes and consequences, insights from past climates, for instance, how unprecedented the current situation is, as it was introduced by the scientific person from the French embassy, but also learning on the slow processes, putting bars on the response of climate system to perturbations informed by our understanding of past climates. And climate models play a key role in our physical understanding. They help us understand the links between causes and consequences, and they are a physics-based tool to explore future changes in response to a broad range of scenarios of future human influence on the climate system. And it is an honor for our community that the Nobel Physics Prize has been awarded to 2 scientists who have developed key methodological advances to explore, to understand our complex climate system. So this is the overall structure of our report. The large-scale climate change, what is observed, how unprecedented it is, understanding human influence, and exploring possible futures at the planetary scale. Then understanding the key processes that shape this response, the carbon cycle, short-lived climate forces that affect global climate, but also air quality and their role at this interface, the global energy cycle, the global water cycle, and the global features that affect sea level related to the ocean and cryosphere. And a third of our report, and this is novel, is dedicated to regional climate information, progress in the methods, understanding of extreme events, and providing information to inform climate and risk evaluations. Going back to the state of the global climate system, our report shows that the recent changes that we all see are widespread from the top of the atmosphere to the depths of the ocean, rapid compared to natural past variations, and intensifying. We are facing novel situations that are unprecedented in thousands of years at the global scale. Let's look at one of the indicators of the state of the climate. This is the average temperature at the surface of the Earth over land and over the ocean. Compared to the late 19th century, a surrogate of pre-industrial conditions, If we look at the last decade, we are now at 1.1 degrees Celsius of warming. So this is what is observed. It is the gray bar. Let's look at the natural drivers. The effect of solar or volcanic activity. It plays a key role on a yearly basis for the response to major volcanic eruptions. It plays a role for decadal variations for solar cycles, but it does not explain any of the centennial trend. Internal climate variability linked to wind patterns, ocean currents, plays a key role on year-to-year decadal variations at regional scales, but it cannot explain at all the observed warming. If we look at human influence, the observed warming is fully explained, our best estimate is 100%, by the role of human influence, with the heat trapping effect of greenhouse gases resulting from human activities, partly masked by the umbrella cooling effect of pollution particles. We have a clearer understanding of the role of every driver acting on global warming. And the two main drivers are carbon dioxide, due to the burning of fossil fuels and deforestation. And the second main driver is methane through a direct effect, but also through its effect on atmospheric chemistry, the formation of ozone near the surface, which is an atmospheric pollutant and a warming gas. They have very different characteristics. Carbon dioxide has a cumulative effect, a very long time scale associated with what we emit in the atmosphere. It interacts with the ocean. The ocean absorbs about a quarter of our emissions, resulting in changes in the ocean chemistry, acidification, potentially harmful for life in the ocean. It interacts with photosynthesis, and the land absorbs about a third of our emissions. However, we show in this report that these natural sinks are affected by a changing climate, and for high levels of warming, they would be less efficient than today. Human influence is the main driver of many aspects: warming in the atmosphere, thawing of frozen soils, the loss of Arctic sea ice, the shrinking of glaciers, a longer growing season over the continents, the uptake of heat in the ocean acidification, and due to the melting of ice over land and the expansion of warmer ocean, it is the main driver of sea level rise. Sea level is accelerating due to a growing contribution of the melt of the Greenland ice sheet and faster flow of specific sectors around Antarctica. So it is now an established fact that climate change that we live with is the result of human influence, and it affects every component of the climate system. But more than that, it is driving unprecedented changes. The current concentration of CO2 is unprecedented in more than 2 million years. The warming I have just shown is unprecedented over more than 2,000 years. In fact, we are gradually getting out of the range of temperature of the current interglacial period, the last 11,000 years, which allowed the development of human civilizations. The rise of sea level is unprecedented in more than 3,000 years. The loss of glaciers is unprecedented in more than 2,000 years. And even the shrinking of Arctic sea ice is unprecedented in more than 1,000 years. So we are entering a new territory for human people. And in addition, we now can show that human activities, in addition to causing global climate change and driving trends in every region, are making extreme events such as heat waves, heavy rainfall events, and drought more frequent and more severe. In every region in red, this is where hot extremes get more intense, And the dots show how confident we are that this is driven by human influence on the climate system. You can see that it affects most of the land areas, and it is also the case for marine heat waves that are harmful for marine ecosystems. For extreme rainfall events in Western and Eastern Europe, Northern Europe, it is intensifying, and it is due to human influence on the climate system. This is because a warmer atmosphere can hold more moisture, around 7% more per degree of global warming. And in regions such as Western and Central Europe or the Mediterranean Sea, droughts are more intense, and this is a double effect. In the Mediterranean area, less rainfall in annual mean, and a warmer atmosphere increases evaporation and transpiration, and therefore intensifies droughts through making soils get deprived of their water content faster. So overland, multiple changes, including compound events, dry, hot, windy conditions that are enhancing conditions favorable for fire. This affects broader regions on longer seasons, and it makes fire weather more severe and more frequent as well. In the ocean, there are compound changes. The ocean is warming with more heat waves as well. It's acidifying. It's mixing less well when it gets warmer, and therefore there's less oxygen going into the depths of the ocean. And these multiple changes affect marine life and people who depend on it. Let's now look at the future. In this report, we explore 5 broad scenarios. Scenarios where global greenhouse gas emissions stagnate during a few decades before reducing. Scenarios where they increase or increase a lot. Scenarios where they decrease or decrease very fast. We also explore the response of the climate system to these scenarios. We take into account not just the projections, but we build on multiple lines of evidence so that we can, for the first time, reduce our uncertainty on the response of the climate system to these emissions. We have reduced the uncertainty range on the response of the climate system to emissions. And we have also a best estimate that is shown, for instance, on these graphs. I just need 1 second because I have lost the pointer to shift the slides. So give me just 1 second so that I can reinstall it. It's almost done. Thank you for your patience. I need to enter just 1 minute. Oh, sorry again. The pointer has vanished, and I just need to enter a specific code so that I can use it again. Give me 1 second. Okay, I got it. Thank you for your patience. This is just a small technical issue. So when you look at our estimates of future warming, what you see is whatever is the scenario, we expect warming to continue in the coming decades. The inertia does not come from the climate system. It comes from existing infrastructure, cars, heating systems, thermal power plants. Even if we reduce emissions, they will continue to add CO2 to the atmosphere, which will drive further warming. However, in the mid-term, you can see that in scenarios with rapid action to reduce emissions, warming can be stabilized well below 2 degrees or close to 1.5 degrees Celsius, which are the goals of the Paris Climate Agreement, and these goals have been developed based on the understanding of associated impacts and risks. You can also see that if emissions stagnate close to today's levels over the next decades, the pledges that have been updated this year from multiple governments, some of the key players are still missing, but from available pledges, emissions would not be on a very high track. They would continue to increase by 2050, 2030. So if they continue to stagnate over several decades, then a warming level of 2 degrees would be surpassed by around 2050. And this would lead to a range of warming between around 2 to 3.5 degrees Celsius by the end of the century, and more than 3 degrees in the next one. So as you can see, what really matters for future warming is the shape of emissions in the coming years and decades. If rapid decreases in emissions occur, a few % per year in the coming years, then it is possible to stabilize warming when global CO2 emissions are at net zero. And as long as global CO2 emissions from human activities are not at zero, then global warming continues to drift, and this drives further changes in every region. Why do I flag every region? Because in every region, we are already facing trends, extremes, values above tolerance thresholds that drive impacts on ecosystems such as forests or cultures in multiple ways. And numerous changes that we experience will increase with further warming. It is the case for the water cycle. A warmer world leads to an intensified water cycle and a more variable water cycle, more variable within a season, but also from year to year. It is the case in the tropics with an intensification of global monsoon precipitation, but it is the case in every region with an increased severity of wet and dry events and wet and dry season, and this depends on the level of warming. Overland warming is larger than the global average, and you can see the higher is the global average, 1.5, 2 degrees or 4 degrees, then the larger is the trend of annual mean temperature in every region. It is also the case for changes in precipitation with an increase in annual mean precipitation in cold regions and a decrease in regions that have a Mediterranean climate. As a result, there is a decrease in annual mean soil moisture around the Mediterranean Sea or in Western Europe. But in cold regions, there is an increase in annual mean soil moisture that gets higher with further warming. What directly depends on the level of warming? Regional warming, the frequency and intensity of hot extremes, of heavy precipitation events, of drought in some regions, the proportion of intense tropical cyclones, category 4-5 cyclones that will, in proportion, will be intensified with further warming. It's also the case for the decrease in snow cover in mountains in the Arctic, thawing of frozen soils, and shrinking of Arctic sea ice. So a key message from this report is that in every region, you need to be prepared to events that you have not previously faced, with larger magnitude, increased frequency, affecting new locations or at different times of the year, and new combinations of events, for instance, coastal flooding together with pluvial flooding as a result of increased heavy precipitation and sea level rise. So we have identified 35 physical climate characteristics which are known to drive impacts and risks. And in our report, you can find how these will change in every region of the world. We also know that we have set in motion the slow components of the climate system, the deep ocean, the ice sheets in Greenland and in Antarctica. And their timescales of responses is very long. Glaciers react over a few decades. They are not yet balanced with today's climate. They will continue to shrink. But for the deep ocean, it's over a timescale of about 1,000 years. and it's also the case for ice sheets. We expect temperature averaged in the ocean to be multiplied by 2 to 8 this century. We expect further melting of the Greenland ice sheet. And because it's melting, then the elevation is going down, and it's a self-sustained process on the coast. Deep uncertainty is associated with the flow of sectors of the Antarctic ice sheet, and we were asked to provide also information not just on our best estimate, but on low likelihood, but potentially high impact outcomes, such as those with an instability of sectors of this Antarctic ice sheet. It is certain that sea level will continue to rise on timescales of centuries to thousands of years. But this will depend on our emissions of greenhouse gases. If you look by the mid-century, you can see that scenarios have limited effect. So we have high confidence on the estimate of sea level rise, but if sectors of the Antarctic ice sheet become unstable, this is our estimate of the possible added contribution on a time scale of several decades to about a century. By the end of the century, the rate and magnitude of sea level rise radically depends first on our greenhouse gas emission scenarios. You can see a factor of 2 by the end of the century between what happens if we stabilize warming below 2 degrees, or if warming reaches 3 degrees or 4 degrees. By 2300, the difference is even much larger, and it's multi-meters differences in sea level rise between low and high greenhouse gas emission scenarios. Over 2,000 years, we're talking about 2-3 meters of sea level rise if warming stays as close as possible to 1.5 degrees of global warming, but 4 to 10 meters for an intermediate scenarios where emissions stagnate in the coming decades and warming is close to 3 degrees Celsius in the coming centuries. So as you can see, the important information is that we can slow inevitable changes, and we can stop those that directly depend on the level of global warming by reducing greenhouse gas emissions year after year in the coming decades. If we do not reduce greenhouse gas emissions, we need to be prepared for an acceleration of sea level rise, an intensification of extremes in the coming decades, and this report provides information on what to prepare for in every region. We confirm a relationship between cumulative CO2 emissions, so past, present, and future CO2 emissions, and the response in terms of global warming. So as said previously, a key condition to limit warming is to limit CO2 emissions, the cumulative CO2 emissions, and this can be translated in remaining carbon budgets. Today, we emit 40 billion tons CO2 per year. This is the amount that has been emitted since the Industrial Revolution. And you can see the small margin of action to limit warming close to 1.5 degrees Celsius or close to 2 degrees Celsius with 50% chance of success or 2/3 of chance of success. So a key condition for stabilizing global warming and limiting the rise of sea level is to reduce CO2 emissions and make it possible to limit the total emissions in the coming years and decades. Other features are to reduce the emissions of other greenhouse gases. And this report places a specific emphasis on methane. Why? Because we are now in a movement to act on air quality. There have been already reductions of emissions of pollution particles, which is good for public health because they are extremely harmful. However, if we reduce emissions of pollution particles only, we will lose their cooling effect quickly. By reducing emissions of methane, which is a potent greenhouse gas, but with a short lifetime in the atmosphere, around 10 years, then we can also improve the benefits for climate reducing the warming effect of methane, and also contribute to improve air quality, because methane contributes to the formation of ozone near the surface, which is also a harmful atmospheric pollutant. And therefore, there are solutions that can help maximize the benefits in terms of limiting warming and also improving air quality. So reducing greenhouse gas emissions, the first priority should be carbon dioxide in terms of its cumulative effect of climate. But a smart strategy can be to use also rapid reductions in methane emissions. And methane emissions come from leakages associated with the use of fossil fuels and, in the world, the growing livestock. So you can see that it's touching different sectors in different regions. If we act now, we would have benefits over a couple of years regarding the concentration of greenhouse gas and pollution particles in the atmosphere, with rapid effects in terms of air quality compared to scenarios with high or very high emissions. For the trend of global warming, it would be discernible from natural variability within around 20 years, and by the mid-century and later for the rate of sea level rise. And this shows the importance of rapid action, as the climate we experience in the future on timescales of the next decades to next millennia critically depends on what we decide to do in the coming years and decades. This report provides you with frequently asked questions, a useful resource, synthesis of climate information for regions, 2 pages, for instance, for Europe. And we also have this amazing resource, an interactive atlas, where you can navigate for a region of interest for you, for instance, Central and Eastern Europe or Northern Europe. And you can look at the multiple changes that will happen in every region as a function of emissions or as a function of the level of global warming or the time horizon. And this information is crucial because it can help plan, it can be critical to do climate stress tests, and it can help better understand what is the implication of global warming for what you care for where you live. With that, I would like to thank you for your attention, and I hope that this presentation has shown how we have taken into account multiple perspectives around the world in shaping the report, in providing the best available knowledge today, not just as a written document, but through actionable synthesis and through an interactive tool that is a critical resource for education and teaching as well. Thank you for your attention.
Dziękuję bardzo, pani profesor, za...
Thank you very much, Professor, for this lecture. If there are any questions from the auditorium, does anyone have any questions? You can ask in Polish or in English. Maciej Wasilewski is my name. I have the following question. Does climate change affect atmospheric pressure? Do they produce anomalies, and how does this impact one's well-being?
Do you want me to answer directly?
Yes.
So yes, of course. Human-induced climate change drives a number of changes in atmospheric circulation. For instance, this is why it affects a decrease in precipitation in semi-arid or Mediterranean areas. This is the outcome of a larger scale change in atmospheric circulation. If you look at Northern Europe, Another consequence is a projected long-term decrease in average wind speed as a result from shift in atmospheric circulation patterns in the northern hemisphere. These are just two examples, but indeed, in a changing climate, there are effects on large-scale pressure patterns. I would like to add one point. Effects on pressure also result from the intensification of the most intense tropical storms. And amongst their characteristics that increase, it is the amount of rainfall, but also the low pressure, which can intensify associated storm surges for this type of extreme events. So these are a few examples that show these aspects. If you are interested in knowing more, please look at our report, especially the chapter 4 on global climate projections, where you will see much more detailed information on these aspects.
Dziękuję za tę odpowiedź.
Thank you very much for this answer. Are there any other questions from the room? I would like to ask you, is there any information in the report on how reforestation, planting forests around the globe, whether that has any influence? I've been reading a lot on this issue, but I can't really find any reliable answer.
This is an excellent question. So in this report, we look at the multiple interplays between forest cover and climate. There are exchanges of carbon, so processes where you increase the land carbon sink will affect the fraction of CO2 that accumulates in the air. However, afforestation also has physical effects that are contrasted depending on the latitude. If you increase the forest cover in the tropics, it tends to have a cooling effect because you enhance evaporation and transpiration, and vice versa if you deforestate in the tropics. In the high latitudes, if you increase the forest cover, because of the albedo, the dark characteristics of the vegetation seen from space compared to the bare soils, you would have a warming effect. So it is not straightforward, and you have to take into account these multiple characteristics. In previous reports, especially the 2019 IPCC report on climate change and land, we have flagged a number of concerns about afforestation. Why? If you plant forests in areas that were previously associated with food production, it can increase the pressure on land, it can affect local people's land rights, and it can also affect food security by reducing the area used for food production. We also stress the fact that these options, they cannot be a substitute for reducing emissions from greenhouse gases. And our report flags the potential, but also the limits purely from a physical science basis. But there are other dimensions that are really important to consider. For instance, if you take some of the largest emitters of greenhouse gases, they cannot cancel the effect of their emissions by planting trees. It is not enough. The available area is not enough to offset the emissions associated with, for instance, aviation or thermal power plants in the world. And finally, afforestation or reforestation interacts with biodiversity. You can restore forests with multiple benefits, with diverse types of trees that are locally adapted and can favor healthy ecosystems. But if you choose cheap options with monocultures of fast-growing trees, you can have negative effects on biodiversity, and you can also have forests that are not resilient at all to a changing climate or to fire risk. And finally, the storage of carbon in a forest may not always be on the long term. So in this report, we flag one aspect of climate action, which is negative emission technologies, so solutions that can remove carbon dioxide from the atmosphere and store it on the long term. And this is really important, the ability to store on the long term. It is not always the case associated with afforestation. So these are some of the key aspects to consider, and we provide aspects in this report from a physical science basis.
Okay, bardzo dziękuję pani profesor za odpowiedź. Musimy już skończyć.
Thank you very much for the answer. Unfortunately, we have to be wrapping up because we have our next lecture coming up. So thank you so much for being with us. We are about to hear a lecture from Guillaume Pitron. Thank you so much to Valérie.